All right. Good afternoon, family and friends. Welcome back. Welcome to my YouTube channel. And today I'm going to discuss with you chemistry and the important topic, which is called reduction and oxidation, combined and commonly known as redox reactions. Now, what are redox reactions? What redox reactions? A redox reaction is a reaction that is made up of two words, and these are the ones that are going to understand. So we're going to look at what is called redox reactions. Now, the word redox is a compound word which is made up of red and ox, which is so today I'm just going to look at the one part. So redox, the red stands for reduction, stands for reduction. Then ox stands for oxidation. So these are two things that we're going to look at. One, there's reduction, and the two, there's oxidation. Yeah, yeah. But I think for today, we're just going to look at oxidation. If time allows, we can even go to reduction. Then later on, we'll come and marry the two, come and merge the two, which is redox. What are redox? Because these two reactions happen together at the same time. Okay, so having known that I've laid the foundation, let's look at the first part, which is called oxidation. The first part, which is called oxidation. Now, what is oxidation? Oxidation can be defined in three ways. Oxidation can be defined in three ways. One, we can talk about the gain of oxygen, or we can say the addition of oxygen to a substance, a chemical species, can be defined as oxidation. The other one can oxidation can be defined in terms of the losing of hydrogen. Yeah, the losing of a hydrogen. When a chemical species loses a hydrogen, that process itself is called oxidation. The other one, there are four other books to split them into four, but I think I'm going to combine the two. The other one is called is oxidation can be defined in terms of losing of electrons. Losing of electrons can also be used to define oxidation. But we understand very well that when an element loses an electron or electrons, they possess. When an element loses an electron or electrons, that element possesses a charge, and the charge is a positive. Before it reacts, the charge is zero. Now, after it reacts by losing electrons, the charge, the overall charge will be plus. So because of that, there is increase in oxidation state. So that one, maybe I can combine, or maybe I can make it be a standalone. But in my explanation, I'm going to combine three and four. The fourth one is the increase in oxidation state. So yeah, so those are four ways in which the process called oxidation can be defined. One, the gain of oxygen. Any chemical species which gains oxygen, that then is called oxidation. If an element loses hydrogen, that is called oxidation. If an element loses electrons, that is called oxidation. And if an element gets to have an oxidation state, increasing, that can also be another way of defining an oxidation process. So because of these four ways in which oxidation can be defined, I'll be mentioning them one after the other with examples on and how we can tell that indeed this is an oxidation state. Four things, do not forget them. One, the gaining of oxygen by a chemical species. Two, the losing of hydrogen by a chemical species. Three, the losing of electrons by a chemical species, which will cause. Four, the increase in the oxidation state, or the increase in the oxidation number. So I'm going to now look at these one after the other. So how can you define oxidation in terms of the gaining of oxygen? How can you define this in terms of the gaining of oxygen? So one, how we can define the oxygen with examples in terms of gaining, gaining of oxygen. Yeah, but there are many ways in which this oxygen can be gained, and one of the ways is having the oxygen alone reacting with an element. Then you combine, you get to have a compound which contains the oxygen. Let's say carbon and oxygen to form carbon dioxide. So carbon dioxide there, carbon has gained oxygen. That is one way. The other way is whereby the oxygen is within the molecule. Okay, I'm going to bring it in a written way. So the gain of oxygen, number one, we can look at examples. Examples in which you can define oxygen in terms of the gaining of oxygen. One, you can have carbon. Carbon react with oxygen, then you form carbon dioxide. So in this example, we have got two chemical species. We have got the carbon, we also have the oxygen. But we are saying that the oxidation is going to be defined in terms of gaining of oxygen. So which one of the two has gained the oxygen? It is carbon. So carbon has been oxidized to carbon dioxide. Why? Because it has gained the oxygen to itself. So in this way, we can say carbon is oxidized to carbon dioxide. One, carbon has been oxidized. Two, the other one is can I use that one is a reduction. Okay, I'm going to use it. You can have carbon dioxide or carbon monoxide plus iron 2O3, then you form pure iron and then plus uh, uh, carbon dioxide. Okay, don't mind the balancing part. The balancing part will come later, but I'm just interested in the gaining and the losing of oxygen here. So if you look at carbon monoxide here, carbon monoxide has got only one oxide here. Carbon mono means one oxide. Then we have got the I've got the ferrous oxide, the iron 3 oxide. Okay, now after the reaction, iron remains alone, meaning all those oxygen atoms that were on iron have been gained by carbon monoxide. So carbon monoxide has gained more oxygen atoms to form carbon dioxide. And this reaction is an example of an oxidation reaction. Why? Because carbon monoxide has been oxidized to carbon dioxide by having more carbon atoms coming towards itself. So in this reaction, we are saying carbon dioxide is carbon monoxide. Sorry, it's carbon monoxide here, which is being oxidized because it's carbon monoxide, which is gaining the oxygen, which was on the iron. So carbon monoxide is oxidized. oxidized to carbon dioxide. Yeah, so that is one way in which you can define the that's one way in which we can define the oxidation by the gaining of oxygen. That is one. Then we're going to define oxidation in terms of hydrogen. Again, the losing of hydrogen. How can we tell that indeed in this? So the most important thing here is telling which chemical species has been oxidized. Oxidized to what? Those are two important things that we have to know. In this reaction that we've got carbon monoxide and ferrous oxide. So which one has been oxidized? Oxidized to what? After it gains an oxygen, what compound is it turning into? So we're saying carbon monoxide here, which has one oxide mono, it has been oxidized by attaining another di. There was one here, dioxide. So we have got now two oxides, from one oxide to two oxides. Therefore, that process itself can be termed as an oxidation process. Then the other one, which is the second one, I think the third and the fourth, I may combine, I may not combine them. We'll see when we get there. So now let's look at how can we define the oxidation in terms of hydrogen, in terms of the losing of hydrogen. How can you tell that this is an oxidizing process, an oxidation process, and it being an oxidation process, and a chemical species has been oxidized from what to what? So two, we can define the oxidation in terms of losing hydrogen. Losing hydrogen. How can we say that in this reaction there is an oxidation process because an element has lost hydrogen? We can speak of ammonia here. We can have ammonia NH. This is a first example, NH3. NH3 reacts with nitrogen. Okay, we have NH3 which reacts with no. I think this let's just show the splitting. Okay, so we have ammonia here. This NH3 is ammonia. Now, during the reaction, what happens is that these hydrogens which are on ammonia will be lost and having the nitrogen remaining alone. So you're going to have nitrogen here, which is a diatomic element, plus oxygen, which is a diatomic element as well. Do not say why here there's one nitrogen here and yet here we've got two. Where is the other one coming from? Always when you're writing the chemical formula of diatomic elements such as hydrogen, oxygen, carbon, nitrogen, you have to take care of the two, because nitrogen cannot exist as a single entity. It has to be combined with another element to form the nitrogen molecule. So because of that, maybe that's when we can we can put in the issue of balancing, whereby saying if here there are two, therefore I'm going to put a two here, but these two I'm putting here will cause an imbalance in number of hydrogen. I've got hydrogen 3 times 2, that is 6, and yet here we only have a 2, and then maybe that what will even force us to put a 3 here to do the balancing, so that people will understand where the 2 is coming from. So if you look at this reaction, what is being oxidized? Which one is losing hydrogen? It's ammonia. Do not say nitrogen is one which is losing. It is the compound itself. In this in here, what is losing hydrogen is ammonia. Don't say nitrogen, because nitrogen itself without hydrogen cannot be called ammonia. So the compound which contains hydrogen, that hydrogen which is lost, is ammonia. So in here we can say ammonia is oxidized. It's oxidized to what? To nitrogen. Why are we saying has been oxidized to nitrogen is that because in here ammonia had the nitrogen with it towards itself. Then after the reaction, the hydrogen is lost, and yet we are saying that the losing of hydrogen by a chemical species, that in itself is called an oxidation process. Yeah, that is called an oxidation process. The other one we can talk about maybe is photolysis. It's photolysis, the splitting of water. When water is acted upon by light, let's say during the process of photosynthesis, the presence of sunlight in the photosynthesis situation is to make sure that this hydrogen, oxygen, this is water, okay, is to make sure that these bonds are broken. And once these bonds are broken, you're going to have oxygen forming. In a similar manner, oxygen is a diatomic element, so you cannot write O alone unless a valence or two minus. But we're not talking about radicals here, not talking about radicals, not valences, we're talking about radicals. So oxygen, when writing the chemical formula for oxygen, you always have to take care of this too. Why? It is because oxygen is also a diatomic element. So once you have that, and then plus hydrogen, which is like that. Taking care of the number of species, here we've got two hydrogens, one oxygen, two oxygen atoms. So I'm going to put a 2 here so that the number of atoms of oxygen will be 2, like we have here. Then hydrogen, we have 2. Here we have got 4. We have got 4. We're going to put 2 there so that we take care of the number of atoms. So now, what can we say about this? Which one is oxidized? Oxidized to what? Okay. Remember, that's the point that I addressed to say when you're writing such an equation, you have to indicate which chemical species has been oxidized. It has been oxidized to what? So in here, the one that contained hydrogen, which has been lost, the hydrogen atoms which have been lost, is water. So we're going to say that water has been oxidized. Oxidized what? Have been oxidized to what? To hydrogen. No, to oxygen, sorry, to oxygen. Yeah. Why have I said to oxygen? Why have I said to oxygen? The reason is this. If you look at this, we are talking about the losing of hydrogen. So the water here is H2O. So once this hydrogen is lost, once these hydrogen atoms are lost, what is it that we are remaining with? We are remaining with oxygen. That's why I'm saying water has been oxidized to oxygen. Like here, we have the ammonia here, but the one which is being lost is these hydrogen atoms. So once these hydrogen atoms are lost, what we are remaining with is nitrogen. That's the reason as to why I said ammonia is being oxidized to nitrogen. Because once the hydrogen remains, once hydrogen is given out, what is it that you are remaining with? Here we remain with nitrogen, here we are remaining with oxygen. So in both situations, we can say that these are what? Oxidation reactions. Why? Because they involve um, um, the losing of hydrogen. Each time when hydrogen is lost by a chemical species, that in itself is called oxidation. The other one is the oxidation in terms of electrons. The oxidation in terms of electrons. Now, what I'm going to say is, if you remember what we said about metals, okay, this oxidation we're trying to define here is going to base on the losing of electrons. When a chemical species loses electrons or an electron, that is what we are terming as an oxidation process. But the question that we need to ask ourselves is that what chemical species is it that is likely to lose electrons? Is it a non-metal or is it a metal? Okay. Those are things that you need to understand. And then there are certain compounds that contain valence, that contain radicals and metals. Such you also need to know how to play around them. So defining oxidation this time around, basing on in terms of losing electrons. Now, when an element loses an electron, the oxidation state increases. That's why I was saying I was supposed to combine these two. Because when an element loses an electron or it loses electrons, there's going to be the increase in the oxidation state, which will be brought about. So I'm going to talk about, I think, two in a multi-purpose way, in a simultaneous way. So how can you explain the oxidation in terms of losing electrons? I'm going to have an equation. Within the equation, I'm going to talk about this as well as the increase in oxidation state, so that maybe we can save time and see how we can marry the two. Talking about in terms of the oxidation state, we can have the reaction. We can have the reaction between copper. You say we react copper, cuprous. Allow me to use the chemical symbols. Yeah, because I know we understand this. I know we understand this. So I'm going to say Cu, which is coming from cuprous, a Latin name. Yeah, cuprous, and then plus oxygen. Okay. No. Let me not use this because maybe someone can get confused due to the appearance of oxygen. Let me say cuprous and then plus okay, let me just say zinc sulfate, lead sulfate. Which one is more reactive? Okay, zinc sulfate. We cannot. Okay, let me say lead sulfate, PbSO4. Yeah, cuprous plus Pb, plumbium, lead sulfate. When this reaction is taking place, we are going to have copper donating 2 electrons to the sulfate, thereby forcing this Pb lead, the lead guy, out of the equation, so that lead is produced as a single entity. Once this happens, the copper is going to take the place of lead attached to sulfate and then forcing the lead out of the compound. So we're going to have copper sulfate plus plumbium lead. But now, if you allow me to combine the two, the increase in the oxidation state, as well as the losing of electrons, how I think that will help us understand this better. So remember, if you are to write the ionic equations, the ionic equation of this compound, if an element is alone, you don't distribute the charges. So you're going to have cuprous Cu plus, here we're going to split because in here we have got Pb2 plus, and then combined with the sulfate. The sulfate here has got a charge of -2. +2 -2, when these guys are combined, there is no overall charge because the charges will be neutralized. Then we're going to form, in here we said cuprous is going to donate 2 electrons to this guy here. So we are going to have in here we've got cuprous, copper with 2 atoms distributed, then plus the sulfate which is 2 minus, and then to form the Pb, which is formed as a single entity. So now once we have that, how can we qualify this to be a redox reaction? We're saying the redox reaction is being spoken of in terms of losing electrons. Which one has lost electrons? After losing electrons, what is it that's been formed? Now, in the law of writing ionic equations, on your left hand side, if you have chemical species that are also appearing on the right hand side with the charges, you cancel them out because those are called the spectator ions. In here, I've got cupra, Cu, no charge. This guy here has a charge. So we cannot cancel them out because this one has got a charge, this one is not charged. So we cannot cancel them out. What about lead? Lead here is charged. On the right hand side, the lead is not charged. We cannot cancel them out. Speak of sulfate, speaking of the devil. Sulfate SO4 2 minus, we have it on the left. If you take it there, we also have it. So what do we say about this guy here? The sulfate is a spectator ion. So we are going to cancel it out like that. So once we cancel it out, or maybe the cancellation is not visible, so what we're going to do, we're going to cancel it out. Can you see it now? Okay. So we're going to cancel this out. And once we cancel out, let's see what we are remaining with. We're remaining with copper plus Pb2 plus, and then to form Cu2 plus plus Pb. Now, remember, this guy here is having electrons within itself. But after this has happened, okay, after this has happened, the number of electrons which copper has lost is equal to its charge. Okay, the same number of electrons that copper had donated, the same number of electrons that copper had donated are the ones that lead had gained, so that it is liberated like that. So what we're going to have here, the one that is losing electrons is a copper. So the copper guy lost 2 electrons. So the copper guy here lost 2 electrons. So Cu2 plus 2 electrons. So these are the electrons that copper lost. So because copper has lost electrons, therefore oxidation is defined because we said that the definition is going to be based on the losing of electrons. And when you see it here, just a minute. Okay, sorry about that. So, in that we're going to say Cu is oxidized. It's oxidized to what? To Cu2 plus after losing 2 electrons. Oh, you can't see too bad. Okay, after losing 2 electrons. So that's what we can say. That in this reaction, copper has been oxidized by doing what? By losing electrons. And the electrons that it lost, how many? There are 2. And these are the ones that lead gained and it was liberated as a metal, like that. That's one way in which we can show the oxidation in terms of losing electrons. If you are to speak of in terms of the increase in oxidation state, how can you speak of it based on the same example? This part that I'm going to say is very vital. You have to take it seriously. When you say the increase in oxidation state, we're talking about the charges that these species are having. Okay, if you can allow me to wrap up to here, when you say the increase in oxidation state, we are talking about the charges that these chemical species possess. So because we're talking about copper being oxidized by losing electrons, now I want to back up my statement by trying to explain the very term oxidation by the means of the increase in oxidation state. So if you consider the cuprous here, if you consider the copper forming Cu2 plus 2 electrons. On the left, when the reaction was starting, how many? What is the charge here? So the charge, the oxidation state, OS, not operating system. State on copper here is 0. Okay, the oxidation state there is 0. And then when this reaction happened, what is the charge on the copper here? The charge is 2 plus. Okay, the charge here is 2 plus. So what can we say about that? So what we can say is that the oxidation state has increased from 0 to 2 because the charge here is 0 and then there is 2. When you have 0 kwacha, you don't have anything. But when someone gives you 2 kwacha, you have gained because see, there is increase in the amount that you have. And we are saying that the increase in oxidation state defines the oxidation. So the oxidation state here is talking about the charge, which is also equal to the number of electrons lost or gained. So this guy here, the number of the number of the oxidation here, the charge is 0, and yet that one the charge is 2 plus. So because of this, we can say copper Cu is oxidized. Oxidized to what? To copper ion U2 plus, which is copper ion. That's how you can define the oxidation in terms of both the number of electrons being lost as well as the oxidation state. So now let's look at another example. Always, I'll repeat, always when you have such a reaction, you have to split the compound into ions, then you do the ionic equation. If you have the ions being present on the left, also being present on the right, you cancel them out because those are called the spectator ions. They're just there to support, to give support to the reactions. In the actual sense, they are not even taking part in the chemical reaction. So let's just look at maybe another example that is coming from the same thing. That's coming from the losing of electrons. Remember, I've been giving examples, 2 examples on each. So we're going to talk about the oxidation, the oxidation in terms of losing electrons as well as the increase in oxidation state. Let's just look at the second example. This second example, I'm going to use different chemical species. I'm going to use different chemical species. I'm going to use different chemical species. But all in all, what you need to understand in terms of losing electrons, you consider metals because metals always get oxidized. And once they get oxidized, once they get oxidized, that's why we say all the transition elements they act as reducing agents. Though I haven't yet spoken about reducing agents, but I'm going to bring it to you later. So the other one, I'm going to use, did I use zinc there? No, I'm going to use calcium plus zinc. This time around, let me use zinc chloride. So zinc chloride, we're going to have something that had happened in the first equation, the previous equation. Zinc will be kicked out. Then calcium is going to donate 2 electrons. And these two electrons are the ones that zinc will gain, and then it goes away. Okay? And then these are the ones that zinc will gain, and then it is liberated as a metal. So once we have that, we're going to have calcium now taking the place of chloride, which you have calcium chloride. It is also 2Y2. It is because the valence for chlorine is 1. The valence for both calcium and zinc is 2. And these are the ones that are appearing here. And once we have that, we're going to have zinc being liberated as a gas. Oh, sorry, as a metal. From there, let's do the ionic equation. What are we supposed to do? Remember, in here we have zinc 2 plus combined with the 2 atoms of chlorine, each having a single charge. Do not write at Cl 2 minus. This is an abomination in the side of chemistry. So what we're going to do here is now we're going to split this. But remember, if an element is a single alone like that, you don't write the charge. Why? Because it has not lost anything, doesn't gain any electron, doesn't lost any electron. So we're going to have the copper, the calcium, plus in here we have the zinc 2 plus because it is supplying the 2 plus 2 electrons. Then plus, remember I said 2 chlorine atom, each having a single charge. And then once this happens, we're going to have now calcium supplying the charge of 2 plus and then plus 2 Cl minus, then plus Zn. Hope you guys are able to write this at your stage. And once you have that, what I'm going to do, remember what I said. If you have the chemical species on the left also appearing on the right, having the same number of charge, the same charge, the same oxidation state, the same element, you cancel it out. Why? That is the a spectator ion. So if you look at calcium, calcium is a standalone. It does not have a charge here. Calcium has a charge. So we cannot cancel it out because it's not a spectator ion. What about zinc? Zinc here, 2 plus. Zn, no charge. We can't cancel it out. It's not a spectator ion. 2Cl minus, 2Cl minus. Because of that, this guy here is a spectator ion. Spencer has to go. And once we have that, now we're going to have calcium plus Zn 2 plus, then you get to have Cu 2 plus, then plus Zn. Now, why in the first place I did not consider the Pb? It is because the Pb had the oxidation state reducing. In this case, if you look around, pause the video and ask yourself, which one of these two, either calcium or zinc plus, 2 plus, has lost electrons? Because we're talking about in terms of losing electrons, which will also bring about the increase in oxidation state. Which one can we say? Pause the video and ask yourself, and then later on you resume to see if you can do this. Zinc 2 plus, from 2 plus to 0, reduction, it has been reduced. The oxidation state is not increasing but reducing. So we're not going to talk about that, but we're going to talk about calcium. So you're going to have calcium here. See calcium, this is calcium, sorry. Calcium 2 plus plus 2 electrons. Why? There are not electrons here, but why am I showing this? It is to neutralize this so that it will be equal to this. Once I combine 2 electrons plus this, it's going to give me the calcium that I have on the left. That's why I'm indicating the number of electrons that have been lost. So if you look here, like the way it was with the copper, here there is no charge on it, so the oxidation state is a 0. What about here? 2 plus. So the oxidation state is 2. So because of that, from 0 to 2, there is an increase in the oxidation state. That's the first way. Then the other one is because here the copper is neutral, copper plus 2 electrons, it has lost 2 electrons. It has been oxidized. One, in terms of losing electrons plus 2, or in terms of the increase in oxidation state. So both ways can help us to identify or to itemize which chemical species has lost the electrons and which one has the oxidation state increasing. So from here we can say that calcium, we can say that calcium is oxidized to calcium 2 plus, which is calcium ion, by how can you define it? How can you justify your statement that calcium has been oxidized by 1 losing 2 electrons, by losing 2 electrons? 2, how can you also justify the statement that calcium has been oxidized by having the oxidation state or the oxidation number, by having the oxidation number increasing from 0 up to 2, by having the oxidation number increasing by increment. Not too sure about the spelling, if A must be there. The increment of oxidation number. Increasing from what to what? From 0 to what? To 2. From 0 to 2. That's how we can tell that that the substance has been oxidized. Yeah, I think that's where I can leave for today. Now, maybe if you can allow me to talk about the oxidation number. How do you tell, or how can you find the oxidation number of an element in a compound? How can you find an oxidation number of an element in the compound? Like, how did I get to know that the oxidation number of calcium, which was in calcium chloride, the oxidation number is 2? How can you tell? It's not by guessing, it's not by CR1 magic, it's not by any other means, or maybe someone just computerized, or maybe someone just conditioned to get to have them done, but you can find the oxidation number of an element when you're given a compound. I think that's a bit, that will be it for today. How can you find the oxidation number? How can you find the oxidation number? So that you can tell that indeed the oxidation number of an element has increased. Okay? How can you tell? Then you should be able to connect to what we have been doing so far on the oxidation being defined in terms of the increase in oxidation number. Okay, so remember what I'm just from doing. If an element is a standalone, it being a monoatomic, it being a diatomic element, the oxidation state is neutral. It's zero. It's zero. Why? Because the element is neutral. So oxidation state. Oxidation state. Other books say oxidation number. How can you determine the oxidation state or the oxidation number in a compound? Um, for I'll say all neutral elements, all neutral. What do I say? All neutral particles. All neutral particles. Particles such as the atom or molecule such as water, ammonia, and nitrogen, a molecule have, but if you can allow me to use OS, have oxidation state 0. We need to note that all neutral elements have got oxidation state which is 0. Example is like the way the calcium was, the zinc, the Pb, the calcium, the copper. If there is no charge, this element is this compound, these atoms are neutral. So because these atoms are neutral, the oxidation state is 0. But what about certain chemical species, such as aluminium ion, aluminium ion, which is Al3 plus. Remember, the charge of an ion indicates the oxidation state. So in here, the oxidation state is 2 plus. Oh, no. The oxidation state actually is not 2 plus. 2 plus is a charge, but for the oxidation state, you start with the charge. So the oxidation state is +2. Yeah, it's +2. Then when you have oxide ion and oxide ion, which is O2 minus. This is an oxide ion, not oxygen atom. Oxygen atom or molecule, we wrote it like that, but it's an oxide ion. So because of that, the oxidation state is -2. This is a charge, but oxidation state, you start with the sign. Which other one? Which other one? The other one we can look at is maybe sulfate. Let me use phosphate. For phosphate ion, which is PO4 3 minus, the oxidation state to be minus 3 equal to the charge. So if you understand this can help us to determine the oxidation state of an element in a compound. So I'm going to look at some examples. I think that's where we're going to end. How can you find the oxidation state of an element that is in a compound? Yeah, that are in a molecule. How can you tell the oxidation state of an element in a compound? How can you tell? So we say, example, how to find the oxidation state in a molecule. So the first one is find the oxidation state or number in, okay, let me say of. So I'm going to use maybe A of sulfur in sulfur dioxide. We're going to consider that. No, not sulfate, in sulfur dioxide. How can you dioxide? How can you consider? How can you find the oxidation state? That one. The other one is the oxidation state of sulfur again in sulfate. B, the oxidation state of sulfur in sulfate 2 minus. Okay. Then the oxidation state of maybe just those two. I think that's where we're gonna end. So how can you find the oxidation state of sulfur in sulfur dioxide? The first thing is this. If you are to split this here, we're gonna have the oxygen whose oxidation. So in here we've got sulfur combined with an oxide. But in here, remember the charge is neutral. So when you add the oxidation state of sulfur, there's no charge. When you add the oxidation state of sulfur plus the oxidation state of the oxide must give us 0 because we do not have anything here. There's no charge. So when you add the oxidation state of sulfur and that of the oxide must give us 0. But just look at if you can go back to what I just indicated, the oxidation state of an oxide. So you are saying sulfur plus, here there are 2, but remember I said one oxide has a charge of 2 minus. Okay, so you're saying sulfur plus there are 2 of these oxides, so 2, and each oxide has got a charge of -2, but the total must give us 0. The oxidation state of sulfur plus the oxidation state of 2 oxides must give us 0. The overall must give us 0. Each oxide has an oxidation state of 2 minus. That's why I've put a 2 minus here. But there are 2. Okay. The O2 is being represented by O2 minus, but there are 2 of them. But minus. But one of these has got a charge of 2 minus. And once we do that, we're gonna have the oxidation state of sulfur plus 2 times -2, which is -4, gives us 0. But okay, so positive times negative is negative. So sulfur, sulfur sulfur minus 4 gives us a 0, but we cannot add these 2. Therefore, this guy goes there. We're gonna have sulfur is equal to 0 plus 4. This is negative. It goes there, becomes 4, and 0 plus 4 gives us C plus 4. So the oxidation state of sulfur is +4. What about in here? It is the same thing. It's the same thing. The only difference is that there are four atoms of sulfur. Okay. So what we're going to do here is that we're going to consider the again consider the okay. You can consider the just a minute. We're going to consider the charge. We said the overall is 0, but in here the overall is 2. Okay, so what we're going to do here is no, supposed to be hydrogen sulfate. Yeah, but it's okay. It's okay then that so that we also look at a different format, the oxidation state of sulfur in here. So what we're going to do here is we're going to do in here is that the oxidation state of sulfur plus how many are they now? 4 of oxygen, 2 minus should give us the overall charge is -2 because that's the overall charge which is there. So that S plus 4 times -2, that is -8 equal to -2. Negative times positive is negative, so we're going to have sulfur minus 8 is equal to -2. We cannot do anything to this because they're unlike terms, so this guy goes there. So that the oxidation state of sulfur will be equal to -2. This is negative plus 8, and that will give us C plus 6. So in this sulfate ion, the oxidation state is equal to 2 minus. And I think